I'm Pedro Chu, and I'm located at the MSC headquarters here in Southern California. So today I'll be talking about contact analysis using MSC Nastran. Here's an agenda of today's presentation. I'll start talking about giving a brief overview of Nastran. I'll talk about what is a contact analysis, then how a contact is implemented in MSC Nastran. I'll do a demo showing you how easy it is to set up a contact analysis, and then I'll come back for some closing comments. So because of time constraints, we won't be able to dive into the theory of contact and the theoretical aspects of it, but you know, you're always encouraged to contact your local MSC office and your local application engineer or hotline support if you have any more questions. Hopefully, after this presentation, you will be, you know, encouraged and excited, as I am, to start exploring more the contact capabilities in Nastran. So let me just start with the overview of Nastran. So the MSC Nastran started in the early 60s. It came out from a project at NASA. At that time, NASA was developing the space program, and each center was writing its own structural analysis package. So NASA wanted to unify and have everybody, you know, in the same platform, using the same software for structural analysis, and that was the start of Nastran, which stands for NASA Structural Analysis. Dr. Dick McNeil was heading that project, and after the end of the project, he started developing his own brand, his own flavor of Nastran, which he started calling it the MSC Nastran. So Nastran can handle from linear static analysis to dynamic analysis to nonlinear structural analysis to nonlinear dynamics, acoustics, optimization, thermal. You know, it can couple these different disciplines together, do a thermostructural, structural acoustics, and so on. Optimization, chaining analysis, and chaining analysis, for example, if you have a structure where you pre-stress or you deform, and because of the new deformed shape, you want to calculate the mode shapes, for example. That would be a typical example of chaining analysis. And so, because of you know, the constant change in the technology, new algorithms being introduced, Nastran is also evolving. It's constantly evolving. We take advantage of high performance. So we have both a shared memory parallel as well as distributed memory parallel. And I think we can say that the software MSC Nastran today is completely different from the original Nastran that was written in the 60s. So this is just to give you a brief history of Nastran and some of its capabilities. So Nastran is the industry standard. You know, the input file format has been adapted by some of the pre and post, many of the pre and post processors, so they can read and write Nastran DAC. Okay, it has been thoroughly, you know, tested and you know, compared results with test results. It's a very reliable in all sorts of analysis, and you can use Nastran to analyze from a very small component to a full vehicle. So we have you know, full airplane is being modeled in Nastran. Okay, so it's a very scalable, and very accurate. So let's talk about contact analysis. So what is contact analysis? We know that everything in life, any structural component will have contact. Sometimes we can make assumptions, simplifying assumptions, to try to predict how the different components are interact with each other. But every time we make a simplifying assumption, we may be losing accuracy in the results. Okay. So when we have complex assemblies, how the load path will go from one component to the next is also very crucial for us to getting an accurate stress distribution. So contact can be used to accurately determine what is the load transfer and load path between components. Okay. So another thing that we need to make sure is that, for example, in this animation that you can see of this seal, something that we call self-contact. Okay, sometimes self-contact may not be important. Sometimes they are very important. And any contact algorithm that you use needs to be able to capture this self-contact. So where do we see contact? Contact that we see everywhere. From the moment that you wake up in the morning to, grab your cup of coffee, you place your cup of coffee, your mug in your table, in your desk, there's contact happening there. Okay. Every time we are handling our mouse, we are clicking at our mouse, there's contact taking place there. But in the industries that we work the most with, automotive, aerospace, heavy machinery, you go from brake pads to airframes to boats, gears, and not only in the classical finite element analysis industries where the finite element started, but if you go to consumer goods, electronics, biomedical, oil and gas, contact is a big component of any problem that we need to solve. So the types of contacts that are available, or how contact started being implemented in finite element codes, we started with node-to-node contact or gap elements. And the gap elements are very time-consuming to set up because we're talking about two nodes, and you need to define a gap between two nodes. And the moment these nodes start moving relatively to each other, you can see that the orientation of these gap elements start changing as well. So it limits how practical these gap elements can be used. That's why in many cases these node-to-node contacts are restricted to small displacement type of analysis. So the next generation of contact analysis was the node-to-segment analysis, in which a node will contact an element face. Okay, so these are more generic. These are our general contact type of analysis. Can be used for linear and nonlinear analysis. It's very easy to set up, and I will talk about this later on during my demo. But the problem is that depending on the geometry, sometimes you may run into some meshing issues where you could have penetration, or even the contact could be missed. Okay, and to solve that problem, then we have the next generation contact, which is the segment-to-segment contact. This is today the state-of-the-art technology, and we can use it for linear and nonlinear analysis. In terms of setup, it's just as easy as a node-to-segment contact, but it is a lot more accurate. So when we implemented the nonlinear contact in Nastran, we wanted to make sure that it was versatile, so that different types of elements could contact each other. And then it was very easy to set up the analysis in Nastran. So basically in Nastran, you don't need to know which areas are going to be in contact. Okay, and again, I'll talk a little bit about this in a few minutes. So the contact implementation in Nastran is very intuitive. It's very flexible. The user has all the controls that he or she needs to do a contact analysis. And basically, the main concept here is that the concept of contact bodies. So if you look at this picture here, for example, this vein, you can see that the green body here would be defined as one contact body, and then blue would be defined as another contact body. And what you can see in this picture here is that the impellers, they have been modeled with PET elements, and the casing has been modeled with hex elements. Okay, so you can see that the meshes are dissimilar. They are not they are disjoint. There are no common nodes between these two different contact bodies. And so some of the features in contact is that we can glue dissimilar meshes. Okay, we can create what Nastran will do is that it will create constraint equations joining the nodes from the impeller to the nodes in the casing. Okay, and also when we implement a contact in Nastran, some of the features are, for example, we can join elements with different degrees of freedom together, so we can have moments being transferred between shells and beam elements to solid elements. So we have two types of contact bodies in Nastran. We have what we call deformable contact body, and deformable contact bodies, they can deform, and thus it can develop a stress and temperature distribution within that contact body. And we have a rigid contact body, where only rigid body motion can be considered. We can use a rigid contact body to apply loads or to act as a boundary condition to my deformable contact body. And to create a deformable contact body, it's a minimal effort. For example, in this example of a bushing and a lug, you can just select all the elements in the bushing as one contact body, and you can also select all the elements in the lug as another contact body. So in this case, we're just showing parts of the contact body in this lug. So you don't have to go and say, okay, this part of my bushing is going to touch or contact this part of my lug. The program automatically will calculate that and take care of that for you. Okay, so that you don't have to be concerned about, hey, if I forgot to pick a few faces or a few on this side here, and then I have a penetration or I have missed a contact and I have to go back and redefine the contact pairs again. So we always recommend that to our customers that when you're doing a contact analysis, just select everything and let the program figure out what is going to be in contact and not. Okay. For rigid contact bodies, then, the rigid contact bodies can be curves if you are doing a 2D analysis, or surfaces if you're doing a 3D analysis. Okay, you don't need to mesh the surfaces or curves that you pick. And as I said, in this case, you can use this rigid body to apply loads to your deformable contact body. Okay, and the rigid contact bodies, they can be, velocity, displacement, and load controls. So the loading can be in the form of, the rigid body moving towards the deformable contact body and so on. Okay, so coming back here to the contact implementation in Nastran. So no contact would be correctly implemented without the friction capability, and we do have two friction models implemented in Nastran. We also have the thermal contact, where you can define two dissimilar meshes and define them as contact bodies, and have heat transfer going between one contact body to the next. And among other things, we have bolt preload as well. Sometimes it's very important that bolt preload is be correctly taken into consideration in your analysis. Also, for thermal contact, we can consider both a steady state or transient thermal analysis. We can do a coupled thermomechanical. So when we have contact bodies, and with thermal analysis, we can at the same time consider the loads being transferred between the different contact bodies, as well as the heat being transmitted from one contact body to the next. And obviously, all the material properties can be temperature dependent as well. So now that we have created the contact bodies, how do we tie these contact bodies together? So the way to tie them together is using contact tables. So for example, let me just turn my mouse visible. So for example, if we have this model, and actually I'll be in my demo, this is the model that I'll be using. We could have 4 springs, and each spring could be modeled as independent contact body. Actually, in my model, I'm not going to use 4 contact bodies. I'm going to use just 1 contact body. But just for the illustration purposes here, so we have 4 contact bodies. We could have a contact body here, a contact table, and in the contact table, that's where I will be telling Nastran that this contact body is touching this contact body touches this contact body, and this contact body touches this contact body. So if I go to the contact table, what I can see is that spring 1 will be touching 2, which is spring number 2. And then I will have spring 2 will be touching spring 1 and spring 3, and so on. So we have, through the contact table, full control over how the contact bodies are interacting with each other. Okay, and for each contact interaction, we have all the options here to specify, how or when the contact will take place. Okay, how far the nodes have to be from the next contact body before they come into contact, as well as we can specify what is the friction coefficient. So I can have different friction going between these 2 contact bodies, and between these 2 contact bodies another friction coefficient, and so on. Okay. So the option that we have in a contact table would be that T for touching, and then as you click on each of these fields, you could toggle between T for touching, G for glued, and blank for no interaction. So that's what contact tables are for. You use a contact table to specify how each contact body are interacting with each other. Okay, and in your analysis, depending on the load case that you have, you could have different contact tables. So load case 1, I could have a certain contact situation. Load case 2, I could have a different contact situation, and then I could use a different contact table. Okay, so now I'm going to go to my demo. So as I said, this is the model that I have. Instead of using 4 contact bodies, I'm going to use only 1 contact body. I'm going to fix my bottom contact body. So basically, I have 1 deformable contact body for the springs. I have 1 rigid contact body for the bottom, which is fixed, and then I have another rigid contact body for the top, and then I'm moving the top contact body 0.1 unit coming down. Okay. So let me bring a Patran. So this is the model that I'll be using here. So I'm not going to go into the mesh generation or anything like that. You know, I got this model from somebody else. I have my elements modeled here. I'm actually using solid shell elements in this case. So basically, it is a shell formulation using solid elements. I have my properties defined already. Okay, so I have this material here, so you can see Young's modulus, Poisson ratio, and shear modulus. I have my properties defined here. Okay, so my properties are basically, because it's a solid element, the only thing I need to define is a material. And then what I want to show you is how easy it can be for you to just create your contact bodies. So I just go to load BC. Okay. And then what I'll do is I want to create a deformable contact body. So I go and define a deformable contact body. So I define a name for my contact body, so I'm just going to call it springs. I define what my element type is going to be. So because these are solid elements, so these are 3D elements. So if you click in here, you can see that your contact body can be either 1D, it can be a beam element, it can be 2D, it could be shell elements, or it could be solid elements. You cannot mix different element types in your contact body, but in this case we have 3D. Notice that I haven't said anything about constraints or boundary conditions for my model. That's because I'll be using my rigid contact body to define the constraints for the boundary conditions for my model. So because of that, the only thing that will be keeping these disjoint springs together will be friction. So what I need to do is I need to go to input data and define my friction coefficient. So in this case, I'm going to define 0.3. Okay. There are a lot other features that options that you can set up in this model, but I'm not going to go over that. I'm just going to use the defaults. And the next step I need to do is I need to select the application region. So in this case, I want to select FEM, and I want to just create a box, all these elements, okay, and then just define my contact body. So I have defined my contact body here, my deformable contact body. Now I'm going to define my rigid contact body for the bottom. So I'm going to rigid, and I'm going to call this contact body base. It's going to be 2D surface, input data. I'm going to say that this contact body is going to be velocity controlled with a 0 velocity in all directions, okay. I have friction coefficient of 0.3 as well. And I'm going to select the application region. Okay, so I'm going to just select this surface here. Okay, notice that it is pointing where my normals are. The convention in Nastran is that the contact will always happen at the bottom side of my surface. So this is the top is this way, so the contact is on this side, so it's the bottom, so this is correctly defined, oriented. So the second contact body that I'm going to define will be the top. I'm going to call this the contact body move. In this case, also it's going to be velocity, but instead of a 0, I'm going to say minus 0.1. And also I define a friction coefficient of 0.3. And I'm going to select this surface, apply. Okay? So I have defined 3 contact bodies, 1 deformable for the springs, 2 rigid for the bottom and the base and for the move contact body. And I'm basically ready to run my analysis. I go to analysis, okay. I'm going to my solution type, and I need to set it to this implicit linear, nonlinear, and make sure that it is a solution 400 that I'm specifying. And then in here, what I need to do is I need to go to contact parameters, and under friction, okay, by default the friction is not on. What I need to do is I need to go and select one of the friction models available in Nastran. So I'm going to select the bilinear Coulomb. Okay. I say OK here. Okay. And basically, that's all I need to do. I don't even need to do to set up a contact table in this case, okay? Because by default, Nastran considers every contact body touching every contact body. Okay. So if I go to my contact table here, you see that by default, every contact body would be touching every contact body, including self-contact. So I don't even have to define my contact table in this case. Okay. Something's going on with the machine here. Okay. So at this point, I'm ready to run my job, and I could just come here and then say apply, and run the job. So instead of that, I have already run this job, and what I'm going to do is just go and select my my results file, and bring that results file into Patran. Okay. Okay, I actually had already attached the results file here, so I can just go to results, and in results I can just let me just come in here and erase geometry, so I can just look at my my deformable contact body, and I can do a von Mises plot, for example. Okay, and you can see in the deformed shape how it is. Okay. Sometimes, because we just to make things a little cleaner, I can go and let's say just look at the one of the springs, spring in the number 2, which is a spring in the bottom. Okay, and I can look at the stresses there. I can look do a marker plot, and I can plot the contact status. Okay, and I can choose the time that I want to plot the contact status. Okay, and then what this is showing me is that these red dots, okay, that will show me which nodes are contacting the neighboring contact body. So the scalar plot is very useful to me. Okay. Because it will show me that only these nodes are touching the next spring on the top, and if I look at the bottom, only these nodes here are touching the next contact body. Okay, and you can do animations. So I could go back here and choose all of these. I don't know how well animation will show over a WebEx, but so you can see the stress is being developed as my spring is deforming. Okay, and there are many other things that you can do with the post processing. Okay, you could plot how the contact forces are being increasing as my top contact body is pressing this spring assembly here. So coming back to my presentation here. So this is what I wanted to show you. So in summary, the contact implementation in Nastran is a general purpose. You can use it for linear, nonlinear analysis, for thermocoupled. It's very intuitive, and the user has a complete control over all the contact interactions, and it's very easy to set up. Okay, again, depending on what you have, you don't even have to define a contact table. You just define a contact bodies, and the program will automatically detect where the contact will occur, and automatically detect the contacts for you. So that's what I had, Srinivas. I don't know if you want to take control back.
Yes, I'll do. Thank you very much, Pedro.